So now we can move on to part B of regression video number 4. And in this part, we're going to be looking at where the X variables, that's the explanatory variables, are categorical instead of numerical. So one of the simplest examples of that is when the X variable is binary. So in the example we were using in part A, we were trying to explain the car's resale price as a function of the car's age and the odometer reading. But another variable we could use is whether or not the car has a pink slip. But just for the moment, we're going to revert to a very simple model where we're just trying to explain price as a function of whether or not the car has a pink slip. Now, if we run this regression using Microsoft Excel, we'll have this being the output, which if I was to put it into a sample regression equation, and you can see I like putting my little hats on the Y variable here to indicate this is an estimated value. And we have 3978 plus 1626 times this pink slip variable. Now, how do we actually interpret this? Well, if pink slip can only be 1 or 0, then think about what happens to this equation when pink slip becomes 1. You're going to get this factor of 1626 being added in to this equation. So to interpret this, you'd say a car with a pink slip would command a sale price $1,626 more than a car without a pink slip on average. And that seems to make sense. But interestingly, if we go back and have a look at our output, you'll see that the p-value is actually quite high. Well, it's certainly higher than 0.1, indicating to us that that variable might not be statistically significant. Okay. Now let's see if we can add in this categorical variable into our mature model series. And here we have model 5, where we're carrying on from model 4 involving both age and age squared. We also have the log of the odometer variable. And notice that our Y variable is also the log of price. So the output here looks a bit like this. Again, pink slip is not significant. You can see the p-value here is 0.3846. So it appears like this variable is not really helping us explain price at the moment. But let's carry on with it. Again, I can put it into a sample regression equation. So there's my 9.237 minus 0.052 times age, etc., etc. And to interpret the coefficient of pink slip in this case, we can say a car with a pink slip would command a sale price 15.6% higher than a car without a pink slip, on average, holding all the other variables constant. So you can see because it's a log of price as a Y variable, this needs to be interpreted in terms of a percentage effect on price. But be careful, I know we like talking in terms of percentages, but when you have this log linear relationship here in a regression, this coefficient is technically the effect in terms of proportions. So that's the proportionate effect on price. So to turn that into a percentage, we know that's going to be 15.6%. And as I mentioned in the video for part A, I'm keeping the technical explanations of logarithms out of these regression videos, but I'll post up a more rigorous mathematical explanation of logs in the description to this video, just for those that might be interested in the mathematics behind it. Okay, let's continue. So that's dealing with a binary X variable, but what happens if our X variable has multiple levels? Now, I haven't included a multiple level categorical variable in the base data set, but instead what I'm going to do is take one of the continuous variables, that's age, and I'm going to split it up into 4 different groups. And these are my borders of each of the groups. So you can see that if I construct these borders at ages of 5, 15, and 35, they kind of exhibit a similar pattern within each of those groupings. You've got quite a deal of high-priced cars that are less than 5 years old. The price reduces a bit between 5 and 15 years. 15 to 35, they're the shit boxes, aren't they? And then above 35 years, you might get a bit of a premium for having a vintage car. All right. So let's at first instance create a categorical variable called ageCat, which is equal to 1 if the age is less than or equal to 5 years, 2 if it's, well, greater than 5 but less than or equal to 15, 3 if between 15 and 35, and 4 if it's in the vintage car category. So here's our regression as it currently stands. And if I was to replace these age variables here with this age cat variable, you might think, well, we're on our way to incorporating a categorical piece of information in this regression. And you'd be right, except for the fact that there's a bit of a problem. Consider what beta 1 is going to represent. Well, if you think about it, that's the effect on price of an increase in the age category of 1 unit. And if you unpack that a little bit, it means that the effect on price of going from the age category 1 to 2 must be the same effect on price as the age category going from 2 to 3. And even more than that, it implies that the effect from going from age category 1 to 2 must be half the effect of the age category going from 1 to 3. So it implies a linearity in terms of these age categories, which we know is just not true. The lowest prices occur in age category 3. So to go from 3 to 4 in our age category implies an increase in price, but to go from 2 to 3 would imply a decrease in price. So there can't be a consistent effect of an increase in age category. So this is where dummy variables come in. And what we're going to do is actually construct 4 separate age category variables. We're going to use age cat 1, which will equal 1 if age is less than or equal to 5, and will equal 0 otherwise. We're then going to use age cat 2, which is the same deal but for the age category 5 to 15. Age cat 3 is equal to 1 if age is between 15 and 35, and finally age cat 4 is for those vintage cars more than 35 years old. So what this means is that for any given car, say a car is 20 years old. If a car is 20 years old, then age cat 1 will be 0, age cat 2 will be 0, age cat 3 will be 1 because its age is between these two values, and age cat 4 will be 0. So with any car, only one of these dummy variables we've created will be equal to 1, and everything else will be equal to 0. So let's see what happens if we were to incorporate all this information into our regression as it stands. So here is age cat 1, age cat 2, age cat 3, and age cat 4. But we're not quite out of the woods yet, because let's just take age cat 1. Age category 1 is perfectly defined by the 3 other age categories. So in other words, if I told you that for a particular car, age cat 2 and 3 and 4 were all equal to 0, you could tell me straight away that age cat 1 must be equal to 1. If the car is not in any of these categories, it must be in this first category, age cat 1. And conversely, if I told you that, hey, there's a car that happens to be in age category 2, you'd know immediately that age category 1 must be 0. Now, this is a big problem, and it's known as the dummy variable trap. And it implies that we can't actually include all 4 of these categories into our model. Now, the statistical reason why we can't do this is that age category 1, when phrased like this, does not add any unique information into our regression model. It will become impossible for the model to tease out whether the effect came from age cat 1 equaling 1 or from the other 3 age cat variables equaling 0. So if you try to run this regression, it will actually not work for you. Give it a go in Excel and create those 4 variables for yourself and see what happens if you run the regression. So to find model 6, we actually have to drop age cat 1. Now, you could have chosen any of those age cats to drop in this case. I've chosen age cat 1 because I think it makes the most logical sense. We're going to be comparing the 3 oldest age categories to the most recent. But there is a bit of a rule that if there is one class that has a higher population than the others, so say there was a whole lot more cars in age category 2 than the other 3 categories, then age category 2 should be your base case, and that one should be omitted. But for the moment, let's just remove age category 1, and let's have a look at the output here. You can see if we scroll down that age category 2 is negative, has a negative coefficient, so does age category 3. Age category 4 is positive. Nothing else has really changed significantly. Oh, look at pink slip. Pink slip is now almost significant. That's interesting. But if I was to write this up into an equation as I have above, you can see I've just put in all of the coefficients in there from this output. Then we might be able to try to interpret the coefficients of age category 2, 3, and 4. So how do we do that? Well, to interpret the coefficient of age category 2, we'll say that holding all other variables constant, a car in age category 2 will command a price 12.9% lower than a car in age category 1. So that's interesting. It means that the coefficient of age category 2 shows the difference between age category 2 and the base case, which is that omitted category. Now, why is that, you might think? Well, for a car in age category 2, don't forget these dummy variables will go 1, 0, and 0. And for a car in age category 1, these dummy variables will go 0, 0, and 0. So hopefully you've noticed the difference there. It's just this coefficient when you start putting those values into this estimated regression equation. So again, we can interpret the coefficient of age category 3 and say that holding all other variables constant, a car in age category 3 will command a price 73.3% lower than a car in age category 1. And for age category 4, we'll notice it actually is an increase over age category 1. So holding all other variables constant, a car in age category 4 will command a price 47.4% higher than a car in age category 1. And these coefficients coincide with the parabolic relationship that we saw between price and age. The middle two categories have the lowest prices, and the age categories 4 and 1 will have the highest prices. But it is interesting, isn't it, that once we actually modeled age as categorical variables like this, our variable pink slip actually became quite significant. Its p-value is only slightly higher than 0.05, so that means it's of borderline significance. So that's something to keep in mind as well. Once you change the functional form of one variable, it does impact on other variables as well. Okay, so let's move on to a discussion about interaction terms in regression modeling. I'm going to start by developing your intuition around interaction terms. And for that, I'm going to introduce just a quick new scenario for you. So this is a little bit of an aside to our model building process. Let's say we want to build a model to explain the salary of all of Google's employees. And let's also presume that we're going to use the employee's age as one of the variables to explain salary. And we're also going to use uni degree as another variable to explain salary. Now, the employee's age is a numerical variable, but this uni degree variable is a binary categorical variable. So it will equal 1 if the employee has a uni degree, and it'll equal 0 if the employee does not have a uni degree. So our presumption here is that, of course, as the employee gets a bit older, one would think that the salary might go up. And this beta 1 coefficient would represent the marginal effect of an increasing age on the employee's salary. So here's our salary on the left-hand side here and the employee's age on the bottom. So no surprise, we'd be expecting an increasing trend. But the idea behind this uni degree variable, as modeled here, would be to say that beta 2 represents the difference between having a uni degree and not having a uni degree. One thinking here that having a uni degree would increase your salary. So that beta 2, in fact, is the difference between these two theoretical lines here, both of which have exactly the same gradient as it relates to the employee's age. Now, if you run a regression like this, you're essentially keeping these two independent variables, age and uni degree, distinct in their impact on salary. However, in reality, we might find that the presence of a uni degree only really matters when the employee is quite young. I mean, if you go to a job interview at age 45, the relevance of your uni degree is not particularly high, is it? What's more relevant is your work experience since. And to allow the model the flexibility to incorporate this effect, we're going to need another variable here, which is the product of the two original variables. So here's beta 3 times employee age multiplied by this uni degree categorical variable. And this one is called an interaction term. But interaction terms in general are required when x1 affects the relationship between x2 and y. So in this case, the age of employee is affecting the relationship between the attainment of a university degree and salary. And it is an extremely common misconception to confuse this with correlation. I kid you not, I reckon about 75% of students get this wrong. They presume that an interaction term is required when x1 and x2 are themselves correlated. But this is completely wrong. The necessity for an interaction term has nothing to do with correlation. So going back to our example, to use an interaction term like this, it's not required that these two variables, employee age and uni degree, are themselves correlated. I mean, think about the reality of these variables. Are older employees less likely to have a uni degree? I'm not so sure, but safe to say any correlation they might have is irrelevant here. One variable merely acts as an effect modifier of the other. So that's the other term for this, effect modification. So one could say that the employee's age modifies the effect of uni degree on salary. But let's take this out of the theoretical realm and apply it to our ongoing model that we're building for car sales. Recall that we were trying to express the log of price as a function of these three age cat variables now, the log of the odometer and whether the car has a pink slip. And I've included in here an interaction term between pink slip and whether the car is in age category 4 or not. Now, why might I have done that? Well, this is where you might have to bring some subject matter knowledge to your regression building. And to be honest, I don't know anything about cars, but this is just a cute example I came up with. So let me explain. Sure, vintage cars might command a premium. So for age cat 4, we might expect a positive coefficient. And indeed, we got one in our first regression. But imagine you had a vintage car that was also roadworthy. In that case, there might be an additional effect. Some combination of the fact that it's a vintage car plus the fact that it's roadworthy gives this car an additional appeal beyond the individual effects of just having a pink slip and being a vintage car. I mean, imagine you could roll the streets in a 73 Tirana or something like that. The fact that you could actually drive it could cause a huge jump in price. So to accord for that, we need to include this interaction term in here to capture that additional effect when both these two variables are activated at once. And here's our output. Notice that some of the p-values have changed a little bit. The original pink slip variable is now insignificant, but this pink slip times age cat 4 variable seems to be very significant. So it seems like we must have done something right with this, but let's interpret these coefficients because it's important to figure out how to interpret coefficients of interaction terms. So here's that expression written out linearly, putting all the coefficients where they should be. To interpret the coefficient of pink slip now, we can't just rely on this variable here. Pink slip actually exists in two places. So what we can say is that for models less than or equal to 35 years old, attaining a pink slip increases the price by 12.3%. So remember that for models less than 35 years old, this is 0. Age cat 4 is 0, so we can forget about this whole last term. We're only going to be focusing on this term over here with pink slip written in it. Hence 12.3%. Now here's the trick. For models older than 35 years, so when age cat 4 is equal to 1, attaining a pink slip increases the price by an average of 149.4%, holding all else constant. Now, where did I get 149.4%? Well, think about what happens when age cat 4 is equal to 1. It essentially just disappears, right? Because you're multiplying it by 1, so this becomes plus 1.371 times pink slip. Notice we also have the original 0.123 times pink slip. So in this case, the effect of having a pink slip would be the sum of both of these put together. So it's 0.123 plus 1.371, which would be 1.494. So I've added these together to get 149.4%. So you can see that the effect of having a pink slip changes depending on how old the car is. If the car is less than 35 years old, the effect of having a pink slip is not that great. But if the car is greater than 35 years old, the effect of having a pink slip is massive. Okay, so just before we move on to part C of this video, it's high time you guys do a little bit of work on your own, just to lock in a bit of the stuff that you've learnt thus far. So what I want you to do is get a pen and paper ready, or alternatively, you can do this in your own version of Excel. But using Model 7, I want you to find me the expected sale price of my 1974 Datsun 120Y Coupe, and it's got 290,000 kilometers on the odometer and a roadworthy certificate, and it looks a little bit like this. She's a beaut. Here's the output from the last model, and it's up to you. See if you can find me an answer for this question. Ooh, and hot tip, the odometer variable, remember, is measured in thousands of kilometers. Alright, so hopefully you've paused the video and you're now back, ready to check out the answer. The regression equation we're using is the one I've listed above. Now for this particular car, it's 1974, so the age category is definitely in age category 4 here. It's more than 35 years old. So we can turn these two variables into zeros and completely forget about them. Age cat 4 is equal to 1. So you can see in my line down here, I've got the constant term, 9.125 minus 0.390. I've then subtracted 0.209 times the log of the odometer reading in thousands, plus 0.123 times the pink slip, which is 1 in this case, because it has a roadworthy certificate. And we also add this extra effect here because it's a vintage car now with a pink slip. All right, so when we add all of this up, we'll find that the expected log of price is 9.044. Now to get to the actual price itself, we have to raise that into the exponential function, essentially unlogging that number. And if we calculate it, we get a cool $8,468, which would be the expected price of my Datsun 120Y. A little steep, you might think, but mate, this thing goes. Now, just a word of warning, I have used the coefficients that have been rounded to 3 decimal places in these calculations. For any boffins who have done this using more precise coefficients, you might get a slightly different answer, but it should be somewhere around 8,468. Stick around for part C, coming up on your YouTube feed next.